Today, we are going to talk about one of the biggest, most fundamental technological shifts happening on the planet right now. It's the complete reinvention of the global telecommunications network. You know, for most of our lives, this network, the thing that connects everything, has been like a closed, monolithic fortress, built and controlled by just a handful of players. But that's all changing. A quiet but incredibly powerful revolution is underway, unraveling that entire old model from the ground up. And what's being built in its place is something totally new. A network that's open, that's intelligent, and that's fully programmable. We're going to dive deep into the crisis that made this revolution unavoidable, look at the incredible technologies that are forging this new future, and explore both the amazing possibilities and, the hidden dangers of this brand new world. So here's how we're going to break it all down. We've set this up like a story in 3 acts. First up, in Act 1, we'll cover the end of an era, where we really dig into what broke in the first place. Then, for Act 2, we'll explore the 3 massive pillars of the solution: this new declaration of openness, the cloud-native revolution, and the quest for autonomy. And finally, in Act 3, we'll face the music. We'll look at the unseen fault lines that are starting to appear and cast our eyes forward to what it all means for forging the 6G future.
All right, let's dive into Act 1. To really get why this revolution is happening, you have to understand that it wasn't a choice. Nobody woke up one day and decided to tear down a multi-trillion-dollar industry for fun. No, this was forced. It was a perfect storm of a failing market, huge strategic risks thanks to shifting geopolitics, and just plain old technological stagnation. The old way of doing things had completely hit a wall. It was a dead end.
Now, just look at this quote. This is not some hotshot startup talking. This is from Ericsson, one of the titans of the old guard, a company that literally built the fortress. For them to come out and admit that the holy grail of network operations, a fully autonomous, self-driving network, was literally impossible to achieve on the old path, well, that's a jaw-dropping confession. It's like one of the chief architects of the old world admitting that their map leads right off a cliff. When you hear that, you don't just need a new map. You need a whole new way of thinking about travel. This one sentence validates this entire revolution. This table right here, it lays out that perfect storm I mentioned, the one that completely stalled the promise of 5G. First, look at the deployment. Most of the 5G you hear about is what's called non-standalone. All that means is it's a 5G antenna slapped on top of an old 4G core. It's faster for your phone, sure, but it completely fails to deliver that super low latency dream needed for things like robotic factories or remote surgery. Then geopolitics created a huge vendor gap, a massive supply chain risk. And this next one is a classic problem. We're amazing at the R in R&D, but we consistently fail to turn that research into actual products that lead the market. But the real kicker, the thing that ties all of this together, is that last row. We simply don't have the expert system integrators needed to stitch together a complex network made of parts from many different vendors. All these problems together created total gridlock. And if you want to see what that gridlock looks like in numbers, here you go. This is the brutal reality. Despite all the hype and all of the articles you read about Open RAN, true multi-vendor Open RAN, that's the dream of mixing and matching the best components like Lego blocks, is projected to be a tiny, almost insignificant slice of the pie, less than 3% by 2028. This is a massive wake-up call. It proves that just publishing some open standards and hoping for the best is nowhere near enough to break the industry's inertia. You need a much, much bigger strategy. Okay, so that's the problem. Let's move into Act 2 and start talking about the solution. The first pillar of this new strategy is a radical industry-wide declaration of openness. The group championing this is the O-RAN Alliance, and their vision is to rebuild the network on 3 core principles: virtualization, meaning it's all software; interoperability, meaning it all works together; and embedded intelligence, meaning the network starts to think for itself. So how does this actually work in the real world? Well, the UK gives us a perfect case study. A major geopolitical decision, the ban of Huawei, basically blew a £2 billion hole in their supply chain. They were forced to make a strategic bet on Open RAN to fill that gap. And they're not just hoping it works, they are backing it with serious money and building a whole support ecosystem, from labs for testing to facilities for building new chips. But, and this is really important, look at the challenge bullet. It's not a magic bullet. This new open approach can use more energy than the old, highly specialized hardware. It just goes to show you that making openness a reality is a massive, all-hands-on-deck effort with real-world trade-offs.
Now, as we're opening up the network, let's zoom in on one absolutely critical component, the user plane function, or UPF. The simplest way to think about it is this. The UPF is the workhorse. It's where the digital rubber meets the road. Every single bit of your Netflix stream, your web browsing, your video calls, it all has to get processed and forwarded by the UPF at absolutely insane speeds. For decades, this was a huge, expensive, proprietary black box, and it created a major performance bottleneck for the entire network. And that is precisely why this is such a game changer. The RAUPF project. Right here, you have researchers using open source software, running on what is basically off-the-shelf programmable hardware, and they built a UPF that performs on par with proprietary systems that cost millions of dollars. Just let that sink in for a second. This is the proof. This shows that the open model isn't just about being more flexible or avoiding vendor lock-in. It can actually go head-to-head with the closed proprietary world at its own game, raw performance, and win.
Okay, so opening up the interfaces between the boxes is the first step. But that isn't enough. The next, even bigger phase of this revolution is changing what's happening inside the boxes themselves. This is the cloud-native revolution. It's about completely rewriting the network's DNA, moving away from a world centered on specialized hardware to a world that is software first. And right at the heart of this shift is the great migration from VNFs to CNFs. Now, the old way, a virtual network function, or VNF, was basically a whole computer with its own operating system running inside a virtual machine. It was a step forward from physical boxes, but still really bulky and slow. The new way, a containerized network function, or CNF, is completely different. Think of it like a tiny, lightweight, self-contained Lego brick. It's fast, it's agile, it's portable, and it's the absolute foundation of how all modern cloud software is built, which of course leads to the big question. You might be thinking, okay, if these container things are so obviously better, why on earth is the multi-trillion-dollar telecom industry moving at a snail's pace to adopt them? And you know what? That's the right question to ask. Understanding this friction, this resistance to change, is absolutely key to understanding this entire transformation. And the numbers, well, they don't lie. This data shows just how slow that adoption really is. We're at less than 20% CNFs today. And even looking 5 years into the future, to 2029, they're projected to make up only about a third of the total. The older VNF technology is still dominant. So what gives? Well, a big part of it is simple organizational inertia. Big companies move slow. But the real reason is the sunk cost fallacy. Operators have already invested billions and billions of dollars in the older VNF technology, and they are really, really reluctant to just write all of that off.
And there's another layer to this problem. The industry is realizing you can't just take the technology that runs Google or Amazon's data centers, like Kubernetes, and just drop it into a telecom network. It's a special kind of beast with unique needs for real-time performance and hardware acceleration. In fact, on the official landscape of cloud-native projects, there isn't even a category for networking. So a group called the CNTI has taken on the mission of figuring out what cloud-native even means for telecom. But here's the catch, and it's that last bullet point. This whole effort will only succeed if the network operators, the customers, actually demand this new way of doing things. It has to be a pull from them, not just a push from the vendors.
Okay, so let's recap where we are. We've opened up the network, we've started rewriting it as software. The result is something incredibly powerful, but also incredibly complex. The old way of having engineers manually type commands to configure everything is just impossible at this new scale. And this has ignited the third pillar of our solution, the quest for true network autonomy. The race is on to build intelligent platforms that can tame all this complexity for us.
And to really get what this quest is all about, you have to check out this brilliant analogy from Swisscom. They talk about two kinds of automation. Bad GitOps is like a paper map. It's where you try to store every single low-level detail, every IP address, every VLAN ID in a file. An engineer has to manually calculate everything. It's brittle, it's prone to error, and it just doesn't scale. Now compare that to good GitOps, which is like a live GPS. With this model,
You only store the high-level intent. You say what you want. I want a cluster here with these features, not how to do it. Then you let intelligent controllers in the network pull that intent and figure out all the low-level details dynamically. It's resilient, it's scalable, and it's self-healing.
And this live GPS model isn't just a theory. It's being built right now with an open source project called Nefio. And here's how it works in practice. Step 1, an operator defines their intent, the what, in a high-level blueprint. Step 2, Nefio takes that one blueprint and automatically generates specialized, detailed configurations for maybe thousands of individual sites. Step 3, it publishes those configs to Get. And then step 4, the magic happens. Autonomous controllers at each and every site pull down their specific configuration and make it a reality. And they don't just do it once, they continuously watch and reconcile, making sure the live network always matches that desired state.
An intent-driven platform like Nefio is what finally unlocks the true potential of AI in the network. And this timeline here shows the incredible progression. Right now, we have AI that can do things like predict network traffic. But next, we're looking at generative AI that lets you configure the network just by talking to it in plain English. Then things get really wild. You've got concepts like NVIDIA's AI factory, where the network literally pays for itself by using its idle computer chips at night to run commercial AI jobs. And finally, you get to research from places like MIT, where they've used AI to achieve 0% packet loss, even over unreliable connections. I mean, that's basically magic. The network is truly becoming intelligent.
And that brings us to our third and final act. Because every revolution, no matter how great, creates new and unexpected problems. As we smash apart that old, closed monolith, new fault lines are starting to emerge. This shiny new world of openness and software has hidden costs and complexities that the industry is only now starting to come to terms with. One of the biggest fault lines is testing. Think about it. In a world with dozens of vendors, how do you make sure all their gear works together? The traditional way is to build a massive, expensive physical lab with all the hardware. It's a logistical and financial nightmare. The solution? It's as clever as it is powerful. You virtualize the testing itself. Projects like SRS-RAN allow you to simulate all the network components entirely in software on commodity servers. You're literally turning the act of testing into code, which makes this multi-vendor integration problem finally manageable.
This new reality leads to a profound and frankly a pretty counterintuitive philosophy for how to operate these huge distributed systems. For decades, the model was always collect all the data from all the sites, move it to a central brain, and then process it there. This quote flips that entire paradigm on its head. In a world with thousands of edge sites generating unimaginable amounts of data, the new rule is don't move data, move code.
This is called the cohabitation principle, and it's built on a very simple truth. Centralizing all that network data is an illusion. By the time the data arrives at the central brain, it's already old news. It's stale. It's like trying to drive through a city using a picture of the traffic from an hour ago. So the new principle is that the code, the intelligence, should live right where the data is being generated. You empower intelligent agents at the edge to make local decisions in real time. This creates a far more resilient, scalable, and secure system. And it gives you smaller blast radii, meaning if one site has a problem, it stays contained there instead of potentially taking down the entire network.
And this brings us to our final destination, forging the 6G future. When you take all these pieces, the openness, the cloud-native software, and the quest for autonomy, and you put them all together, you're not just improving the old network, you are laying the foundation for something entirely new. The sources are really clear on this. 6G isn't just going to be about faster phones. It's a much grander vision for a programmable planet, a world that integrates sensing and communication from the ground all the way into space, and is built around core missions like sustainability, security, and digital equity.
So there you have it. We've journeyed all the way from a broken, closed, and stagnant system to witness the birth of a truly open, intelligent, and software-defined platform. We've seen how a crisis forced a revolution, and how a global alliance of builders is rebuilding the network piece by piece with code. The great unraveling is almost complete.
The rebuilding is well underway. The global network is, for all intents and purposes, becoming a single, intelligent, programmable computer the size of a planet. Which leaves us with the only question that really matters now. What are we going to ask it to do?